In most practical applications, there are multiple constraints that influence the choice of material. How do we factor these into the material index? Connecting rods in high-performance engines are critical components. They must be strong, yet lightweight in order to minimise inertial forces and bearing loads. When minimising cost is the objective, they're usually made out of cast iron because it's so cheap. But what are the best materials for conrods when the objective is to maximise performance? We translate the design requirements into the function, constraints and objective, except this time we have more than one constraint. It must carry a peak load F without failing by fatigue or buckling. We assume the shaft has a rectangular cross-section. The objective function is now an equation for the mass that we approximate as this. The fatigue constraint requires this inequality to be satisfied. Therefore, the mass of a conrod that will just meet the fatigue constraint is this, with a corresponding material index. We then apply the buckling constraint from scratch. From this, we obtain a second equation for the mass and a second material index. The conrod must meet both constraints. We assess which constraint is active for a given length. Short conrods are prone to fatigue and long ones are prone to buckling. Setting the two equations for the mass equal gives the equation of the coupling line with a coupling constant C. Materials with the optimum combination of mass 1 and mass 2 are identified by creating a chart with these on the axes. Beryllium and its alloys are the obvious choice, with titanium alloys coming second for short rods and magnesium alloys coming second for long rods. Carbon fibre reinforced plastics are also suitable materials, however manufacturing limitations mean they are still only prototypes.